This model is a classical case of pattern recognition. We use the MINST dataset in which in this model, MINST dataset basically contains images of handwritten digits. The digits value range from 0 to 9. These images are converted into features using their pixel values. The value of the pixel being black, then the value of the feature would be 1, and the value of the pixel would be white, and the value of the feature would be 0. We use SVM to model this data set. SVM is basically a supervising learning algorithm. SVM works on the concept of hyperplanes. Say we have two independent variables and one dependent variable whose value can either be A or B. If we plot all the data points on the xy plane, in an ideal scenario, all the data points that classify as A would be on one part and classify as B would be another part. Therefore, we could create a hyperplane in this case, which is a line which could divide the regions into perfectly into two parts. Now this line is chosen by the value of a support vector, where the support vector is in this xy plane. As the support vector is basically a point that is closest to this line and closest to this line. So therefore, there can be multiple lines that can be drawn in this region to divide the region into the two classifications. Therefore, we use the concept of maximal margin classifier to choose the value of to get the equation of this line. What the maximum margin classifier is, that the distance between between the hyperplane and the support vector should be maximum. SVM can work on both linear models and non-linear models. In case of a non-linear models, it will convert it into a linear model and then create a model on it and then revert it back. There are two hyperparameters in SVM known as C and sigma. C is known as the cost, and sigma basically dignifies the amount of non-linearity of the model. The higher the value of C, the higher we allow the misclassification of data points, and the higher the value of sigma would be, the higher the more complex or more non-linear we want our model to be. In this scenario, we chose SVM over other models because of huge number of factors. We do not use logistic regression in this, because simple logistic regression can only have two outputs, that is 1 or 0, and as we have values of 0 to 9, that is 10 classes, we did not use simple logistic regression. In case of multinomial logistic regression, we did not use that, as because we know logistic regression does not work very well with non-linear data, and as we have multiple features in this, therefore we cannot say that each and every feature would have a linear dependency with the dependent variable. Therefore, we did not use a logistic regression model. In case of our decision trees, we do not use decision trees, as the amount of factors, again, because decision trees can have a specific amount of length. If we have a huge amount of depth in a decision tree, then basically it would hard code for each and every data point. Decision tree is a non-linear model, while logistic regression is a linear model. We evaluated the model, basically we created a model or the using two different kernels, that is the RBF kernel and the linear kernel. When we use the RBF kernel, we got higher accuracy, therefore we use the RBF kernel. Now, to tune the hyperparameters in the RBF kernel, we use the logic of cross validation. Cross validation is basically the concept in which we take a proper set of the value of C and the proper set of value of sigma, and then we are using those values of the hyperparameters. It is a model is created on the subset of the data set, and when the model is created, that model is then tested on the other subsets. So, and whichever proper pair of C and sigma gives the proper accuracy, we will use that value of C and sigma. That is how the cross validation is done. So we then using the RBF kernel, we got a proper value of C and sigma using cross validation, and then the final model was then put onto the test data points. Then we got an accuracy basically of 96%.